All right, so we'll get started here. Can everyone see my screen properly? All right, cool. We are the interns, innovative nerds transform engineering for refueling networks in space, and we created Project Heroes, which is helping to enhance the refueling of orbiting empty satellites. I'm Brent.
I'm Jade.
I'm Rory.
I'm Trevor.
And I'm Tyler.
Before we get started, I'd like to give a great shout out to our mentors, Sarah and Libby, and put any questions you guys have in the chat while we're presenting. All right, so we'll get started here with our requirements and assumptions. So before we really get into the project, we had to make sure we knew exactly what we were going to be talking about and what we actually wanted to do. So first we created a list of requirements for what we were actually going to do. So we wanted to create a design for a new multi-tool that would be able to refuel floating satellites that no longer have any fuel. So then we had to research and develop this idea behind what is a refueling satellite? What is it actually doing? And then we worked through that engineering design process to figure out and create a final CAD model, which we could deliver and animate today through this presentation. While going through this design process, we made sure there was a few assumptions to limit the scope of our project. So first of all, the main frame of the satellite is essentially already built. So on the top image here, you can see a mock-up of 2 satellites we created to import our tool into just as a test to see how it would kind of fit. But we didn't actually design like the main part of the satellite. And then we're also assuming the satellite we are actually operating on is mostly already done with maintenance. So we're not really fixing anything beforehand, just focusing on the refueling here. We're also assuming the satellites are attached in a system. So if you were spinning off something on the other satellite, it's not just spinning the entire satellite, it's only taking that thing off. We're also not considering launch or landing like coordinates where we're going in space. We're only considering the part of where the satellites are already connected and ready to start refueling. So first of all, we'll go with our space debris from Rory.
One of the big concerns that we had to address with our design specifically was the problem of space debris. And right now there is a large amount of orbital space debris polluting space's environment. And this really creates problems when launching new satellites, because the problem is that the more satellites that are launched into space and eventually become space debris because they run out of fuel, the higher possibility of satellites, there is a higher possibility of satellites colliding with either each other or with space debris. And this is terrible for the entire space industry. For instance, in 2009, a Russian satellite and an American satellite crashed into each other over Siberia, and this created a gigantic amount of orbital space debris because both satellites were destroyed. And for our design, we wanted to really emphasize limiting orbital space debris. So one of the main things that we tried to do and succeeded in doing was making sure that we reused the cap, which Tyler will explain in our concept of operations next.
Okay, so after doing some basic research on this topic, we found that there's a series of 5 steps that needed to be done in order to properly refuel a satellite. So the way the fuel is kept in a satellite is there are 2 caps. There's a cylindrical and a hex nut cap that are each secured by their own wire to prevent them from coming loose during takeoff. And there's also a seal at the very end beneath both caps that prevents the fuel from leaking out into space since it is very corrosive. So the 5 steps are just to cut the first wire that secures the cylindrical cap, remove the cylindrical cap, you need to repeat the same process for the hex nut style cap. And then finally, you need to turn the hex valve in order to have access to the fuel tank in order to start pumping fuel in. And next is Brent talking about current prototypes of refueling satellites.
So throughout this project, we did a lot of research on other refueling satellites that have already been tested. So an example of this was OSOM-1, which is a refueling and servicing satellite that was created as sort of a design to create a system throughout Earth's orbit to maintain older satellites and make sure we could keep reusing it. So this was an interesting project to look at since it aligned with our initial problem that we were trying to solve. The other thing we looked at was the RRM series, which is a series of 3 missions throughout 2013 and 2018. And what this essentially was there was a arm on the ISS that was operating on a test satellite, not in space or not in free flowing in space, to essentially test their valve and how to undo these caps. So they're they were essentially testing what we want to apply on a real satellite. But something we saw with this is that it could potentially be very complicated and create a very large satellite that would be orbiting the Earth, since they constantly went back and changed their tool on the robotic arm rather than all having it on one tool. So that's something we thought maybe we could improve on that. So after going through all this research, we ended up starting our engineering design process, which Trevor's going to talk about now.
A bit about our engineering design process. As it starts is we had to define the problem, which was the great amount of space debris in which we wanted to delegate by refueling some of these depleted satellites. Reusing these tools would be a helpful add-on to what we could do. We all did background research on this topic, and we created a scope for specific requirements in which we wanted to specifically work on. We had brainstormed our own ideas and sketched them out. We had developed some prototypes in CAD, which we had tested those solutions through them CADs, and we tested the parts and redesigned them as we made this final CAD product, and we are now communicating our results about that. And we're going to talk about our sketch designs. We're going to start off with Rory's scissor design.
So we each made our own individual designs to model a solution to the problem. I was personally inspired by the idea of using scissors and a jack screw to make my design, and it is a multi-axis pivoting arm that is operated with scissors, and it is manipulated by a jack screw, which is powered by an electric motor. And then in our final design, we used the concept of turning the screw with a motor in conjunction with one another. And next is Tyler with his design of the tripod.
So my design was, I designed it in order to have the least amount of movement in the robotic arm as possible, and to always make sure that the probing refueling mechanism is always strictly in line with the valve. So how it works is that there's 3 different tools. There are 2 cap grabbing mechanisms and a wire grabbing mechanism that are all connected to arms about a hub that can then rotate from a motor. And one of the things that I had most difficulty with this was the grabbing mechanism. So how I envisioned it to work was that there were going to be 3 arms, each is inside a gear that when turned follows grooves patterns that always makes sure that the cap is directly in line with the center of rotation. And what we could take away from this design that we put in the CAD is that there needed to be at least 3 points of contact with the cap in order to properly unscrew it. And next is Jade with her double header design.
So for my design, I got the idea off of a wishbone structure. And so my design is a multi-tool with one side having a claw and then the other side having a refueling device. Both of them would be able to retract in and out as well as rotate individually and as a whole by one large motor at the base. My design also influenced the final design by thinking about having external valve to connect to the main valve. Here is Brent with his design of the robotic arm.
So this design is mainly inspired by common robotic tools that you see in stores. So what I wanted to do was use a small amount of motors to get as many axes of movement as possible. So I have one motor that is clamping down on the cap, one motor that spins that to be able to rotate and pull off the cap, and then also a motor that will rotate the entire arm to store the cap to another side of it. And something we kind of took away from this was that you're going to need a lot of different movement options while operating on a satellite in space. So we ended up kind of assuming that there was going to be, at the start of our tool, a robotic arm that would be able to manipulate it properly, which you can see in our final CAD later. And here's Trevor with our hub design.
So a little bit about my hub design is that I wanted to make it as mechanically as possible. So it's ran entirely off of a motor and a solenoid, in which kind of operates like a car starter. And that solenoid is what disengages and engages the hub. And when the hub is engaged, the tools can be selected to its desired tool. And then when it's disengaged, the tools will be inserted into the motor or onto the motor shaft so the tools can be operated. This specific design as the claws in which will grip onto the caps and remove them and retain them. The wire cutters were designed off of an angle gear and which would move the blades up and down. And this here was a base start to our design, which we modified it to perfection and using all these other designs to add on to this. We're going to have Rory talk about our weighted matrix, and which helped us decide on this.
In order to really figure out which of our individual designs was going to be the best choice for us to use as the baseline for our final CAD, we created this weighted matrix to rate our designs. And it is an unbiased way which creates categories such as efficiency, feasibility, and energy usage that are weighted the heaviest out of 15. And then there are other criteria such as the center of rotation, electrical wiring feasibility, and the type of materials that it was to be made out of that are weighted lighter because we determined that those are less important. And then we rated each individual part of our design according to all of the criteria. And then we multiplied that value by the weight of the category that we gave the category. For example, Trevor's hub design received a value of 120. In the efficiency category, you can see that in the blue box, because we determined that the efficiency category was one of the most important categories and should be weighted the heaviest at 15 out of 15. And then his design earned an 8 out of 10 for how efficient we thought that it was. So we multiplied that value of 8 that it earned times the 15 that the category was worth, and that earned him a value of 120. At the end, we added up everybody's values, and we found that Trevor's design, the hub with a overall value of 919, was the design that we wanted to use for our final CAD. And next is Brent with our model of our final CAD.
So while working through this project, we ended up on this final CAD, which you can see here. There's a panoramic view of our satellite environment with all of our assumptions, and then our tool, which is color-coded by the different tools, and also the hub design, which you saw we actually based this entire thing off of. So during this process, we all created different parts of this design, which you'll get to see more of. But to actually do this, we ended up having a CAD schedule. So this CAD schedule is color-coded, with the darker colors being a higher up part of the assembly. So there's, for example, the cap removal arm in pink down there, but then you have the sub parts such as the grips or the arms, and then you also have sub assemblies like the outer shell, which then have sub parts under that with compressible side and casing. And since we are all working collaboratively together on this CAD, we assigned different people to each one, how many of them there would need to be in the final assembly, when it needed to be done by, and then finally, if it was completed. So we started with red, where it was not completed and not started at all, yellow when it's in progress, and then green once it's finally done. So let's start getting into each part of our design, starting with the claw design.
So a bit about our claw design. This specific image here is of the triangulated claw, which was redesigned from the square claw. This is because the square claw had 4 arms with 4 grips, and which would work just fine for a cylindrical cap. But when we realized that we had to get a hex nut cap off, we obviously it wouldn't work to have 4 arms on it. It wouldn't sit flush on the cap or on the hex cap. So what we did is we redesigned it as a triangulated shape, and each of these arms set flush on the cap so that it could obviously remove it. The way these work is it has a faceplate in it in which the grips can maneuver within it. And when the faceplate is depleted by the caps, it is moves the arms together to grip onto the cap. This specific animation on the top is of the square cap or square claw, in which clamps onto the cylindrical cap to remove it. The latch design is there at the bottom, and which shows in which the mechanical latch we needed to have so the cap would stay in the claw and not be lost in space. So obviously we didn't want to add power to this and add complications. We designed a mechanical latch in which sort of works like a pen. If you deplete the face a little bit more, it will unlatch itself and let the cap go after it's back on the satellite. So we're going to have Tyler talk about our wire cutter design.
So for the wire cutters, the main things to keep in mind when we were designing this was that it needed to be small and so it could be easily maneuverable, just because the wire in each the wire position from satellite to satellite will vary. So it's very important to keep it small so that way, no matter what condition the wire or position the wire was in, we could always cut it. The blade we designed to be concave in order to make sure that the wire doesn't slip out as it's being cut. And the way it operates is that there's a blade that's connected to a screw. The screw, once it's engaged to the motor, can then turn and it will either move the blade backward, releasing the wire, or forward, cutting the wire, depending on which way it was being turned. And next is Roy with the refueling device.
So the animation that you're seeing right now is mainly just a placeholder for a refueling device that we might actually use with our tool. We modeled the CAD and the animation mostly from the refueling tool that we saw a lot in the RRM missions. In order to work, the tool rotates to engage the fuel valve, then it moves forward. It unscrews the next cap, it pumps in hydrazine fuel, and then finally it replaces the cap with a part that keeps the fuel from escaping from the valve. And next is Brent, who will talk about the hub design.
So to sort of unite all of these tools together, we obviously had to have some kind of base that allowed it all to work together. And so since part of the main piece of our design was that it was all mechanical besides one motor and one solenoid, we ended up with this base design here. So this base essentially works by having a motor that spins a gear, and then once it's at the desired tool, which during this animation it would actually go to the wire cutter, which isn't shown here, so you can see how it works better. So then once it's at that desired location, the solenoid will then drop down so that the hub lowers down, the motor will engage the desired tool and then start spinning that tool without actually rotating the hub. Then once it's done with that tool, the solenoid will be able to raise back up, engaging the gear, and then the motor would spin to the next tool that was required. So after all of this CAD, all of this project, we had a lot of hard skill takeaways that I think Trevor's going to talk about now.
Yes, we definitely had a lot of hard skill takeaways in which we can take away and use later in life. One of those main things being drafting and CADing. Most of our team had never had experience with CAD, in which we first time we've ever used it was for this project. And now at the end of this, we're definitely proficient at it and can pretty much CAD whatever we would like. That hard skill takeaway can definitely be used later in life. The idea of drafting an idea from just thinking and putting it down on paper is quite the experience to be able to see that turned into at least a sketch, and further from that, a CAD model, and then further from that, developed into a prototype or made into a real object, and it can yield even further from that. So there's a lot that we can go and take away from this as simply making a product that can be used in everyday life. So we also had some soft takeaways, in which Jade's going to talk about.
Yeah, so when it comes to soft takeaways, everybody in this group definitely has different ones, but three main that all of us can probably agree on are public speaking, friendship, and teamwork. When it comes to teamwork, when we joined, we weren't really sure about the work ethic and if everybody had the same. But then once we all figured that out, we used our strengths and we sort of built that as our foundation of this project, which leads me to talk about the learning environment. So for the learning environment, we definitely learned how to efficiently communicate during COVID and this new environment as well, and sort of despite not knowing each other in the beginning, and also doing this entire project virtually as well. We met 3 to 4 times a week, depending on what needed to be done. We also had extra work days on Discord to see if anybody needed help. They can just pop on, just text and see if anybody could help them. And then for our schedule, like you see above, we talked with our mentors and they helped us come up with the idea to break down a large topic into little detailed topics to then see what needed to be done every week. At the end of this internship, I think that all of us can agree that we are one big friend group now, and that we're doing what we like to do as a team, and that we're all glad to have this learning experience. So here are the resources, and I will post the link in the chat if you want to see more.
Thank you all for listening. And if you guys have any questions, feel free to ask them now.